Hello, we're back in the second video in this series, and I just wanted to evaluate some numerical exponential expressions first on this video, and maybe even the next, and then we'll start to get into numbers and letters. We'll throw in some algebraic looking things in there. So let me just start with these ones, 2 to the 4th power. What does that mean? Well, remember, by the definition of exponents, it means that we're looking at 2 times 2 times 2 times 2, if you expand it out. And so in the end, we get 16. Okay? You could say 4 times 4, or 8 times 2, or however you like to look at that, or you could just go 1 by 1, but in the end, you get 16. Now, what about this guy? It has a negative inside the parentheses, and so what this is telling me is that everything in this parentheses is to the 4th power. So again, if I were to expand this out, what I'm looking at is negative 2 times negative 2 times negative 2 times negative 2. And notice what happens there. We have 4 negatives being multiplied by each other. These two become a positive. These two become a positive. You could say positive times a positive is a positive. So in the end, we get a positive 16. And it turns out that this is going to be true whenever we have a negative in the parentheses to an even power on the outside. Why? Because we're multiplying a negative number an even number of times, and that always produces an even number. So we don't have to worry about that as much with the odd powers. And I guess I could take a moment just to say one more thing about this that might help in evaluating the next one. I could say that this negative 2 we could look at as negative 1 times 2, right? We all agree negative 2 is the same thing as negative 1 times 2. Now, why would I even want to look at it that way? Just to point out something interesting here, that if we have negative 2 to the 4th power, I can say that that's the same thing as negative 1 times 2 to the 4th power. And then we can distribute the power to the powers of those numbers. Now, I don't know if I said this previously. I don't think I did. But anything to the 1st power is itself. Okay? Just generally speaking, anything to the 1st power is itself. I can say that these numbers have the power 1 up there, and then distribute the power to the powers. In fact, I could put a parenthesis around this negative 1 and say it's to the 1st power. Now, if I distribute the power to the powers, then it looks like this. Negative 1 to the 4th power times 2 to the 4th power. 2 to the 4th power is 16. That's what we set up there. Negative 1 to the 4th power is negative 1 times negative 1 times negative 1 times negative 1. So this gives me positive 1 times 16, which is just 16. And it may be helpful to think about the negative in this way, especially in future examples involving more complicated things. But so, okay, that's an interesting way to look at it. What does that mean about this guy? Negative 2 to the 4th power. Well, first thing I want you to agree with me about is that this is the same as negative 1 times 2 to the 4th power. Is that true? Negative 1 times anything makes it negative itself, right? So certainly that appears true. But what this is telling me is that this negative actually represents a multiplication that's occurring. So we've got multiplication and we've got exponentiation. We have an exponential here. Now remember your order of operations, the exponential comes first. So I'm evaluating this. This becomes then negative 1 times 16, which is negative 16. And when I look at things like this, I just like to say to myself, oh, okay, the exponent only applies to that 2, not to the negative sitting there on the outside. Why is that different from the one above? Simply because of these parentheses. Okay, the parentheses are telling me that anything inside here is getting the 4th power. It's to the 4th power. But this one, only the 2 is, the negative's hanging out on the outside. So be aware of that and watch out for that. Again, this difference is really only present with positive powers. If you look at negative powers, then you get the same thing either way. But I wanted to illustrate the difference. So let me just give a few more examples, numerical examples of using the definition of exponents in the exponential form. And let's just see what they look like. Suppose we had a fraction go with blue. Although my blue's not working too well. Suppose we had 2/3 to the third power, let's say. If I expand that out, it's 2/3 times 2/3 times 2/3. Or I can use the other property that says I can distribute the power to the powers of these guys. Their powers are 1 if you don't see it. So when I distribute that, it looks like 2 to the third power over 3 to the third power. And that comes out as exactly the same as 2/3 times 2/3 times 2/3. So this gives me 8 on the top. 3 to the third power is 27. And of course, it is nice to know your powers as you're going through evaluating exponential expressions. But if you don't, that's okay. Just review it or expand it out. Do whatever it takes. Let me give you a few more examples. Suppose we had, boy, I'm just getting stuff everywhere. Looks a little bit crazy. Suppose we had a couple negative things, like 2 to the negative 1 plus 2 to the negative 2. And by negative things, I meant negative powers. Well, can we just add these together and somehow put that power together? No, not exactly. Remember by the negative exponent rule that what this really represents is the following. 1 over 2 to the first power plus 1 over 2 to the second power. The negative exponent rule tells me that I'm looking at a fraction, really. And it's 1 over this thing to the positive that power. 2 to the 1 is just 2. 2 to the second power is 4. So this is the same thing as 1/2 plus 1/4. And then you proceed as usual. Of course, we need a common denominator. So I'm going to call this 2/4 plus 1/4, add it up to get 3/4 in the end. Okay. So more fun playing with numbers. Let me just erase all this and hang out with me for a second or a minute while I do it, or fast forward through all this erasing action. Wiping action, I don't know. Okay, there we go. And now the dry rag. First the sort of wet one, then the dry one. Do-do-do-do-do. Good way to clean things up. Can apply that to many things, I suppose. All right, there we go. I just want to put a few more numerical examples down before I start getting into algebraic stuff. Suppose we had something like this. Let's just say 2 squared plus 3 squared. Well, this is simple to evaluate. This gives me 4 plus 9. Again, don't forget your order of operations. Exponents before addition. And 4 plus 9 is 13. Now, the reason why I wanted to illustrate this is to contrast it with the following. What if I had 2 plus 3 in the parentheses squared like that? How would this come out? Well, again, order of operations tells me let's do that stuff in the center first. 2 plus 3 is 5. Square that means 5 times 5 gives me 25. I just wanted to drive home that this really does give you a different answer, and generally speaking, it does. There may be a case where you get the same answer and you can have fun with that. But remember, if there's a plus sign here, if you have an x and a number or something like that, you cannot distribute the power to the powers. Only when they're being multiplied, only when it's a product, okay? So let me go on. How about, let's multiply something. 4 times 5 to the third power. Again, this is just an order of operations game. Exponents first. This becomes 4 times 125, which gives me, looks like 500. Okay. How about more fun with this? A fraction to a negative. Let's do 3/4 to the negative power, -2. We can use that property that says, oh, we can flip over that fraction on the inside and rewrite this as having a positive power on the outside. That's one way to do it, and it's a fine way. This gives me then 4 squared over 3 squared after I distribute this power to the powers of those numbers, which is 16 over 9 in the end. Let me show this a slightly different way to illustrate something else that I want to get to. Okay, so same example. I'm going to start with that 3/4 to the -2. You can, if you'd like, distribute that power right away. And depending on how complicated this inside of the parentheses is, you may want to do that. Let's take a look at what that would look like here. 3 to the -2 over 4 to the -2. Now that's kind of interesting because 3 to the -2 all by itself is 1 over 3 squared. And 4 to the -2 all by itself is 1 over 4 squared. So what this represents, one way I could write it is like this. 1 over 3 squared over 1 over 4 squared. Okay. Wow, that looks weird. And I could evaluate those exponents right now that I have them in a positive exponential form. But I'm going to keep those exponents there just to show you that this really is the same as this in the end. Remember that every fraction bar you can think of as division. So what this really says is I've got 1 over 3 squared divided by 1 over 4 squared. And this may be a notation that looks a little bit more familiar to you when you're dividing fractions. That's why I put it this way. And it turns out that an equivalent expression is 1 over 3 squared times 4 squared over 1. Remember that dividing fractions is the same thing as taking the first one and multiplying by the reciprocal of the other one. I remember a little phrase, copy.flip, and this can be shown easily from here, and take some time to prove that if you'd like, just because it's fun to prove things, especially when you're doing nothing instead of except watching TV, which is really not good for your brain. Okay, so how about 4 squared over 3 squared? Yeah, maybe some TV is okay, I don't know. And in the end, that gives you 16/9. And I'll show some examples where it might actually be beneficial to distribute here first instead of flipping it over like we did over there. But I just wanted to show the equivalence of these two things. So let me stop this video for now, and I'm going to continue and start adding more to these examples. I'm going to start putting letters in there, other numbers, and just try to make it a little bit more complicated and have a little bit more fun with these exponential rules.